Okay, so thanks so much for everyone to coming like online Causal Inference seminar today. We have a great speaker, Jared Murray from University of Texas at Austin. He's going to talk about a unifying weighting perspective on causal machine learning, causal methods, Gaussian processes, and Bayesian tree models. And he has his co-author, Avi Felder, in the Q&A session. And after the talk, we're going to also have a discussion from Rahul Singh from Harvard University. And Sarah is going to handle the Q&A. So Sarah?
Yeah, I just wanted to remind you to please use the Q&A function instead of the chat so that Avi can answer your questions. And then if at the end there will be still questions that Avi hasn't answered or you still want to ask new questions, then maybe Jared and even Avi and Rahul can discuss about them. So I will read them out for you at the end, okay? So then with this, Jared, the floor is yours.
Great, thank you so much. Let me get set up here. While I'm getting set up, I just want to take a second. Thank everybody for joining today. These virtual talks are so much better when there's an actual audience. And then I also want to, oops, screen. I also want to thank our discussant who has put something together based on a half-baked typo-ridden draft at the last minute. I haven't seen it, but I'm sure that it's fantastic and far better than what I would have done with the same source material. So thanks, Rahul, for volunteering to do that and then dealing with my borderline incompetence along the way. So this is work that is in progress, progressed a fair amount, but still very much work in progress. So I'd very much appreciate any feedback here in the talk or afterwards from folks. Joint work with my colleague Avi Feller, who was able to join us for the panel today. He'll be in the chat answering all your fantastic questions. Big thank you to Avi also for making a big push here at the last minute so we could get these slides together. So let me just jump right in. The title here is ambitious. I want to make a couple sort of caveats from the outset. This is a unifying weighting perspective. It's not a universal weighting perspective. So there are a lot of really interesting causal ML methods that are not going to sort of fall in this framework that we're talking about today. But there's an awful lot that do. And through the course of working on this project, I have learned a lot about the existing literature. Including work from a lot of fantastic folks in other areas. But also I've learned a lot about my own work, kind of mapping it onto this weighting perspective and then seeing how it lines up with all these other methods. So hopefully you guys will get something out of that too. So let's just set the stage here. If you're on this call, probably I don't need to explain to you that we've seen a pretty steep rise in the application of machine learning to causal inference. I would say one of the biggest advances in this space over the last 10, 15-ish years has been really just recognizing that adapting machine learning methods that are so effective for prediction to the setting of causal inference is not as simple as just picking something off the shelf, changing the inputs a little bit, dumping it into some causal black box, and then hoping what we get out the other end makes sense, right? All sorts of issues with that in practice. So a lot of work from a variety of different people on adapting causal machine learning, or sorry, adapting machine learning to causal settings. A lot of that work based on traditional semi-parametric theory and new flows. There's the work on double machine learning, all sorts of semi-parametric efficiency type arguments being made for machine learning methods adapted to the causal space. There's a couple of pretty big, I don't know if you call them drawbacks, but areas for improvement, right? The first one is that these are largely black box methods, right? So concurrently, there's certainly been a lot of work on trying to interpret machine learning methods. A lot of that stuff also adapted to causal inference. But when we're talking about causal inference, we're really talking about an area where transparency is at a premium, right? What are we doing when we answer causal questions? Well, usually we're not going to stop there, right? It's part of a larger feedback group where we're trying to answer causal questions to decide about policies or interventions to deploy in practice. Maybe these estimates of heterogeneous effects are being fed into machines that are actually making decisions about who gets treatments or interventions. And so it's really important to be able to interrogate these things. Another thing that is near and dear to my heart as a trained statistician is that we have just fewer sort of traditional type diagnostics, right? I spend a significant portion of my life teaching regression to people that maybe should never actually use it. And we spend a lot of time talking about diagnosing model assumptions, when these things are reliable, when they're not reliable, et cetera, et cetera, et cetera. And the suite of tools that we have available for doing that with Causal ML is lacking. So in parallel with this causal machine learning world, unfortunately, in my perspective, there's another box that people are putting some of these methods in, and that's the Bayesian non-parametric causal modeling, Bayesian machine learning universe. The literature is a little bit bifurcated here. However, it has sort of broken through in that, at least empirically, in these large empirical evaluations, Bayesian methods seem to do really well. And in particular, Bayesian methods based on regression trees seem to do really well. We see it empirically. We have a little bit of theory sort of informing why that might be the case. But I would say that overall, we don't necessarily have a great understanding of why that's the case, right? So there is this perspective that these methods are sort of distinct from the broader causal machine learning literature. You think about the advances that have been really influential in that area. You're thinking about things like the R learner. You're thinking about things like double or debiased machine learning, one-step augmented estimators, kind of all the same thing when you squint. And it turns out that those things are all very closely related to the work that we're doing on Bayesian tree models. Now, looking at these things from a Bayesian perspective doesn't necessarily fix those last two drawbacks or areas for improvement we talked about on the last slide. This is still very much a black box. You might even argue that the box is a little bit blacker because we're trying to use a full posterior distribution to learn about these things. And there are very few diagnostics, in particular, very few diagnostics that are targeted to things like causal assumptions. Okay. So that's some of the things we're going to try to address, right? So what are we doing in this paper? What we're doing is we're looking at the implied weighting representation for a variety of causal ML methods. And we're going to focus on methods that rely on the Robinson transformation or the Robinson kernel, which I'm going to introduce you to in a minute here. Okay. So there's a deep connection here between the Robinson transformation or outcome models and the Robinson parameterization. And things like balancing weights from the classical causal inference literature, which ties directly into all the fantastic and exciting new work on estimating Riesz representers using regression models to infer weighting functions. We'll see a little bit more specifics on that in a minute here. Okay. So I'm going to show you a few things about those. I'm going to show you that when we move into the Robinson parameterization, there's some nice things that happen. We can take the implied weights and we can pull them apart into two terms that are doing two different things. One that is trying to balance functions between a treatment and a control group to control for confounding. Another piece is trying to shift the target. So if we have IID samples from a distribution P, but we want to estimate the average treatment effect in a different distribution, say Q, there's another component of the weights that's actually dealing with that transfer. So you can think about that as transportability. You can think about it as generalizability. You can think about it as covariate shift. It's all 6 of one or a half dozen of the other. Okay. I'm going to draw out the correspondence between Gaussian processes and kernel ridge and what I call conditional posterior weights. Okay. This is a correspondence that has been used in simpler models for a long time in the survey sampling context. It's a little bit of work around this in the causal context, but I'm going to extend that explicitly to the non-parametric Bayesian causal models that are widely used in practice, BART, BCF, things like that. And then I'm also going to show you what happens when we take those models and instead of just using them off the shelf the way they were introduced, if we move them into the Robinson parameterization. Okay, so I'm going to illustrate that with Bayesian causal forest. As a wholly unbiased consumer of the literature, I think that's one of the better methods out there, so it makes sense to take a closer look at that one. Okay. And then finally, I'm going to show you some standard weighting diagnostics, and I'm going to apply them to causal ML methods, in particular to that RBCF model, just because it's going to illustrate some points. But one thing I'm probably not going to have time to talk about today is the other advantage of putting all these things in a common framework of weighting estimators, which is that we can compare these methods that are fit or inferred or built in very different ways. We can sort of put them all on common footing if we can derive a weighting representation, and we can use that to compare between methods and glean a deeper understanding of how they're similar, how they're different, where they're different, and why they might be different where they're different. A lot of words there. Okay, so I'm just going to step quickly through some background here. You guys are in the online causal inference seminar, so a lot of this is going to look familiar to you. We're going to start by making some causal identifying assumptions. So over here on the left, oops. Let's try this. Just trying to get my pointer. Can you guys see my cursor? You can? Okay, great. I'll just use the cursor. Okay, so the causal setup here, we're going to start with some standard identifying assumptions. In particular, we're going to assume strong ignorability plus SIFA. Right, so I've got all my confounders measured. I've got no interference. I have all that good stuff. On the right-hand side here, I'm going to define a couple of quantities. The first one is going to be what I call the outcome function. So that's going to be the conditional expected value of each of my potential outcomes, conditional on covariates. We're just going to call that f of x and z. That's going to be an object of great interest in the talk. And then this little e of x down here, that's just going to be my propensity score, the probability that z is equal to 1, given that x is equal to x, right? So a lot of what I'm going to tell you here is going to transfer to other interesting settings, multi-arm treatments, continuous treatments, things like that. But it turns out that this is hard enough to do that we're just going to focus on this simple case. So layering those assumptions together, plus some integrability assumptions, is going to lead us to what I call a structural model for observables. Okay, so this yi over here on the left-hand side, that is the observable y. Those are not my potential outcomes. And under these assumptions, I can say that yi is f of xi and zi, right? So zi here being a binary treatment indicator, plus some error terms. The error terms have this structure down here. They are conditionally independent of treatment assignment, and they have conditional mean 0. And that's it, right? So when I make reference to the structural model, I'm really referring to the model that you see here on the slides. That's before I start layering on parametric assumptions, making assumptions about the form of f, whether it lives in a particular function space, whether I can express it as a regression on some basis, et cetera, et cetera, et cetera. Okay. So pretty mild assumptions there. Again, it's really ignorability, consistency, and then some means existing. Okay. So the estimands that we're going to look at are going to be average treatment effects in a target population Q. So another thing that I could talk about today that I'm not going to have time to talk about is estimated conditional average treatment effects, right? So you can think about that in this setup as taking that target distribution Q and taking it down to a point. There's a lot of regularity conditions that fall apart when we do that, and I just don't want to deal with them today. So we're going to imagine that we want to estimate the average treatment effect in a sort of proper distribution Q here. So this setup is going to accommodate the ATE in the original population P, the ATT, conditional estimands that assume a fixed distribution for the covariates. It's going to cover an awful lot of stuff. Okay? So my estimands are going to be right like this guy down here, right? So the ATE under the distribution Q. I have IID observations from P. Lurking in the background here, there is an assumption that Q is absolutely continuous with respect to P. You can relax that. It doesn't really matter too much. But the first big point I want to make about our estimands is that it's a linear operator given by a linear operator on the outcome function f. Okay. So in addition to ignorability, SIFA, all that stuff, you guys are causal people, so you know what's coming next. I need some kind of overlap assumption. My overlap assumption is going to be that this is a nice linear operator, in particular that it's continuous, which is going to mean that it has a Riesz representer in L2. Okay. So I'm just going to go ahead and state the overlap assumption in terms of the Riesz representer. The Riesz representer is defined as follows. That's this alpha Q of x and z. Can you guys still see my pointer? It's like disappearing. You can? Okay, I can't. It's weird. How about over here? Can you see it over here? All right. It's like I didn't live through COVID. Okay. Oh, good enough. So the Riesz representer here for our target estimands, it looks a little bit strange, but you've seen each of the two pieces before. So over here on the left-hand side, underlined in red, those are just good old-fashioned inverse propensity weights signed by the treatment group. You're going to see why I added the sign in a second here. It's really going to help us out with notation, right? So on the left-hand side, underlined in red, we have inverse propensity weights. What do the inverse propensity weights do? They deconfound, right? So they mean balance functions between treatment and control groups. On the right-hand side, underlined in blue, we have a density ratio, right? What's the density ratio going to do? It's going to mean balance things between the source, P, from which I have IID samples, to the target Q, where I want to estimate my average treatment effect, okay? So we're going to try to do both of those two things at once. So sometimes I like to call this composite overlap assumption, because it's accounting for two things, right? It's accounting for I need some treated and control units in the places in covariate space where I want to estimate effects. It's accounting for that density ratio there. Overlap can fail in that I can have propensity scores going to 0 or 1, as long as Q assigns 0 mass there, right? So I'm not making a strong overlap assumption. Well, this is a strong one, but it's not as strong as the ones you might see elsewhere. Okay. So like I said, alpha Q is the Riesz representer in L2P. And the important thing is really down when we get down here to down here. So tau Q, I can write as a population level weighting estimator. So I can take observations Y that are distributed according to P, or really the triple X, Y, and Z distributed according to P. And tau Q is going to be the expected value of alpha XZ times Y under P. Okay. Now the Riesz representer has some other nice properties. The Riesz representer has what we call balancing properties. So by definition, for any f that's mean squared integrable under P, we have the following relationship. The expected value of the Riesz representer times any potential outcome function f that's integrable is going to be equal to, on the right-hand side, the expected value in Q of the contrast f of x1 minus f of x0, right? Of course, on the right-hand side, if f is our true outcome function, then on the right-hand side, I have tau Q. But that's going to work for any function of f and z that is integrable. Okay. Now, if you're a weighting person, you're used to thinking about different forms of balance. Okay, so this general balancing property that holds by the Riesz representation theorem implies a couple of balancing properties that are more familiar to weighting folks. Okay, so in red, again, we're going to be leaning on those inverse propensity weights to do what? To take functions of x and mean balance them between treatment and control groups. That's going to deal with confounding, right? We're also going to, the Riesz representer is also going to mean balance those functions h of x between my source population P, from which I have IID samples, and the target Q, the population where I'm trying to estimate an average treatment effect. Okay, so those properties in red and blue are implied by the more general one up top. You can put those things into one-to-one correspondence if you want. But really, I just want to draw out that this balancing property of the Riesz representer, which looks a little bit abstract, is actually equivalent to what a weighting person would naturally want their weights to do. Okay. So that's just some setup. What I'm going to do now is I'm going to briefly review the weighting representation of outcome models. Okay. So lots of different ways that we could try to estimate tau Q. One way is the weighting form that I showed you a few slides ago, right? I know that if I hit Y with alpha X and Z and take an expected value, I get back tau Q in the population. So I could try to build those weights directly. The other thing I could do, of course, is I could estimate an outcome function and then take my estimate of the outcome function, integrate that against Q, looking at those contrasts. I could do an augmented estimator that puts those two things together. We're going to talk about outcome models today and draw the equivalence between outcome models and weighting estimators. You can close the loop and get back to augmented estimators. Long line of work on that. We're not going to today. So let's just start simple. So what I'm going to do is I'm going to begin in a setting where I just assume that I have a simple regression model. So my estimate for f of x and z is just going to be a linear regression in some features that I compute from the observed covariates and the observed treatment assignments. Okay. So think about the estimate that you would fit in LM, right? So I have a bunch of things I want to control for. Maybe I want to estimate some heterogeneity by interacting x with z. We could also get sort of arbitrarily fancy here. We could be using basis expansions, et cetera, et cetera. We'll build up to that. And I'm going to start by estimating that model in about the simplest way that I could, using a ridge regression estimate of my coefficients, right? Y ridge, Maybe I'm in high dimensions. Maybe I want to regularize. We could get back OLS estimates by taking sigma squared going down to 0, and everything I'm about to show you will go through. Okay. So it turns out that if I go ahead and fit this model, okay, what am I going to get? I'm going to get an estimate for the coefficients that's over here on the right-hand side, right? So these are my regression coefficients. If I want to get a prediction at x and z, I compute my basis function at x and z and hit them with the regression coefficients. Right. Now, of course, what I get back at the end of the day is going to be a weighting estimator, right? Those regression coefficients are linear in y, so my predictions are linear in y. So what I have here are a set of model implied weights, right? I have a linear smoother. We all know that ridge, OLS, regression, those are linear smoothers. That's just what this means. Now, what does that mean when I go to estimate a causal effect? If I wanted to estimate a causal effect in this model, what would I do? Well, I would do something very similar, right? I need to estimate my f hat. I need to plug it in to the equation over here, right? So now I'm plugging in f hat for the true f, computing that integral over 2. How does that work out? Well, over here, I can just pull out my regression coefficients. And so really, I need to hit my regression coefficients with this quantity here, phi delta q. Okay. So phi delta q is just the expected value of phi of x1 minus phi of x0, right? So the feature vector when I set the treatment equal to 1, the feature vector when I set z equals 0. Okay. You might hear these called counterfactual features. We're going to be looking at this contrast here. This guy phi delta q, it's kind of an interesting object. It turns out that's actually the Riesz representer of that linear operator in a different space, in a Hilbert space. Not going to be super central to what we're doing here, but you guys will see in a second why that's sort of interesting. So what does that mean for my treatment effect estimate? It's going to take this form. Again, I'm going to hit my regression coefficients with phi delta q. And I'm going to get back model implied weights. Okay. So this is not something that I invented for this talk. This is well known. Oftentimes you see it explicated in simpler contexts where maybe we're just trying to estimate the mean in a different population. We're trying to transport a mean. Maybe we're just trying to deconfound. We're trying to do a couple of things here at once. So the problem is going to have some more interesting structure that we'll get into in a second, right? But for now, what's the takeaway? The takeaway here is just that we get back model implied weights. Okay. Whoops. Too far. No, just far enough. We're going to spend a lot of time talking about kernel ridge regression. Okay. So kernel ridge regression is just a generalization of the regression model you just saw to allow us to have infinite dimensional features. Okay. If you're not familiar with kernel ridge, I'm not going to teach it to you in 5 minutes, but there are some simple correspondences here that will help you keep track of the notation of the rest of the talk. Right. So when we go from parametric ridge to kernel ridge, what are we doing? Well, we're going to estimate instead of a set of regression coefficients. We're going to try to directly estimate a function f that's going to live in Hilbert space. The Hilbert space is going to be a reproducing kernel Hilbert space that's determined by the kernel that I use. Oh, that's a mouthful. The correspondence here between function evaluations, where before my predictions in the regression model were just the inner product of this feature vector, phi x and z transpose beta hat. We're going to have a similar thing going on here in the kernel ridge regression, except now my inner product is going to be happening in some Hilbert space. And on the left-hand side, I'm going to have a feature vector that's determined by the kernel. This is the canonical feature vector, if you're familiar with that literature. It's going to act very much like the coefficients in my regression model. Okay. And then on the right-hand side, we have f hat. That's a point in function space. You can think about f hat as just determining regression coefficients. Okay. And then at the end of the day, when I estimate tau hat q, how am I going to do it? I'm going to do it in the same way. I'm going to get that phi delta q, what we call the target representer. That is the Riesz representer of that linear operator in this Hilbert space H. And then I'm going to hit it in the inner product with my estimated f hat, the same way that I did over here in the parametric regression model. Okay. So if you're familiar with kernel ridge, that's not news to you, none of this. If you're less familiar with kernel ridge, you can just impute transposes for all the inner products on the rest of my slides, and you will get 100% of the message. Okay. Oh, yes, before we move on, down here in orange, it turns out that we're also going to get back a weighting estimator when we compute our treatment effects in this way. Okay, so we're going to have an estimate that's linear and wide. Okay, so let's take a closer look at what those weights actually are. Okay, they have a simple closed form. Okay. So it turns out that we can write them as the expected value with respect to an empirical distribution. So that little p hat down there is just denoting that I'm taking an empirical average with respect to the sample values of x, z, and y. Okay, so you can think about that as an estimate of the population expectation. On the right-hand side, I have for you the closed form of that function alpha hat. Okay, it depends on this object c hat. That's a covariance operator. Again, if we're thinking about the regression model, it's the uncentered covariance or the scatter matrix of those features phi. Okay, we're going to take a closer look at that guy in a second. Okay. So that should look familiar to you guys. It probably looks a little bit like regression coefficients, and effectively they are, right? So by fitting that outcome regression model, I'm getting an estimate of f hat. F hat is going to live in that RKHSH. It's also going to imply an estimate for the Riesz representer. The estimate for the Riesz representer is going to live in the same space, and it's going to have a very interesting form. Okay. So where does that closed form come from? There are a few different ways to derive it. Okay. So down here at the bottom of the slide, we can derive it as an estimate of a regularized estimate of the Riesz representer under the population Riesz loss. Okay. Rahul's written 15 papers about doing this. They're fantastic. This is a known thing. But it's a really clean way to see that implied estimate of the Riesz representer as doing something eminently reasonable, right? So the first term of that loss, I'm just going to try to minimize the mean squared error of my estimate relative to the truth. Then on the right-hand side, I have the same kind of ridge regularization that I used in kernel ridge. So I'm going to encourage that estimate to be smooth in a way that's going to decay in the sample size. Okay. Again, I want to emphasize that the estimate we get back is going to live in the same model class or the same function class as the one that I assumed for f. That's going to be important later on. Okay. So that's one way to get at this estimate for alpha hat. There's an equivalent form in terms of balancing weights. Okay. So the balancing weight objective is going to look something like this. Similar basic idea. We're going to have two terms in this penalty, one that's going to apply regularization, one that's going to encourage accurate estimation, one that's going to encourage accurate estimation. In this case, we're going to encourage accurate estimation by trying to minimize the worst case imbalance. Okay. So if you guys remember when I showed you the properties of the Riesz representer, the Riesz representer in L2 was the unique function that satisfied the interior of this soup, right? So if we just look inside of these absolute values here, this was the balancing property that was held by the Riesz representer, and it was held for any function h that's in L2, okay? Now we could try to minimize the soup over L2 directly. It would be a loser's exercise. So what we're going to try to do is we're going to try to optimize for minimizing the worst case imbalance over a different function class. That function class is going to be determined by the outcome law. Okay. So if you're a balancing weights person, what are we going to try to do? We're going to try to balance the features that are in our regression model. Okay, and it's going to have this weird form of imbalance in the inside here. Again, that's going to imply mean balancing between treatment and control groups, and then target balancing from my source population P to the target population Q. Okay, so the leading term there is worst case imbalance in functions H that belong to the RKHS. I'm going to try to minimize the whole thing, again, over the same function class as my outcome model. Regularization over here, again, is maybe a little bit more direct, right? So on the right-hand side here, you can think about this guy as the variance of my function estimate with respect to P. Okay. I haven't enforced that this thing is mean zero, but it is. Right. That's also going to control the variance of my weighting estimator in the case that I have heteroscedastic errors. Right. But for right now, you can just think about these two optimization problems as doing the same thing. I'm trying to accurately estimate alpha Q while I apply regularization. All right, so now we're going to get specific. We're going to think about how to specify that function class. We're going to move from generic models of the outcome to what we call R parameterizations. Okay, so first I'm going to do that for you at the population level with the true F, right? So on this slide, F is the true outcome function for my structural model. I can always rewrite that function in what I call the Robinson or the R parameterization. Why do we call it that? We're regressing on the residuals on the right-hand side. So that Z minus E of X, that's the residual for Z in the propensity score. If I slide that M of X over to the left-hand side, then I can think about this whole outcome model as regressing residuals in Y on residuals in X. And I'm going to do that with heterogeneity, right? So I'm going to let tau of X be a function of X. Okay. So that's completely general. Some hinky things happen if I don't actually have overlap, but let's go ahead and assume that I do. In that case, it's completely general, right? So this is not imposing parametric assumptions on the true outcome model. It's just sort of rearranging things in a way that's convenient for us. Okay. Now, if I want to reparameterize my assumed outcome model, I'm going to do more or less the same thing, right? So remember, we started initially with this parametric regression model. F of X was phi of X and Z transpose beta. Okay. If I want to move to the R parameterization, I can do the same thing, right? So I can rewrite the right-hand side in this form where now I have two regression functions, M and tau. Tau of X is going to be the regression function that gives me back Kate's conditional average treatment effects. M of X is going to be a nuisance parameter that's going to be a regression function giving me E of Y given X. Okay. So tau of X I care deeply about, M of X I care less about, but I need to deal with it. And just to kind of make explicit what we're doing here, what we're doing is we're taking that feature vector and we're partitioning it into two pieces. The first piece, the M of X, those are the regression coefficients in the function M of X. That is the stuff that we're going to try to mean balance between treatment and control. Okay. And then down bottom, my features are this weird looking thing that is Z minus E of X, so the local residual in Z. And then times the heterogeneity features phi tau, the ones that feature in the heterogeneity function down here. Okay, so this form looks a little bit weird, but it's very, very useful to write things in this form. Right. Now, if I wanted to do that, and I didn't want to be working in the parametric setting, what do? I can do the same thing in kernel ridge by just saying I'm going to let M live in some Hilbert space HM, tau live in some Hilbert space H tau. Both of them are going to be reproducing kernel Hilbert spaces with their own kernel. Okay. How do I get there? It's just the same thing as doing kernel ridge with this nasty looking kernel down here. Okay. So if you're a person who understands kernels, you already knew what that kernel looked like. If you're somebody who's less familiar with kernels, this picture doesn't help you, so I'm going to move on, but it's there, right? So it's just kernel ridge with a very specific kernel, what we call an R kernel. The thing to keep in mind is that it's going to give me a parameterization of the outcome model that is in the Robinson or regression-on-residuals form. Okay. So what does that mean? So I can move from a generic outcome model to an outcome model that's in the Robinson parameterization, right? Well, we know that moving from a model that's generic to one that's in the Robinson parameterization here, it's going to do the same thing to my implied estimate of the Riesz representer. Okay, I dropped a Q here, but this alpha hat Q is my estimate of alpha Q. So it's going to have the same regression form, right? So there's going to be that MA of X out front and this tau A of X that's multiplying the propensity score residuals here, right? So it's going to have the same functional form. That's what we saw just before we started talking about this parameterization. Now, what's interesting is that if we think about the true Riesz representer in L2, it's already in this form, right? It was just maybe a little bit hidden because that function MA of X, that nuisance parameter in my outcome model, it's exactly equal to 0, okay? And then on the right-hand side, all I've done is kind of rearrange things so that we have a term hitting that residual. So MA is going to be 0 almost everywhere at X. And this TA regression parameter is going to be a product of 1 over E of X times 1 minus E of X. You can think about that as a measure of local overlap, right? If overlap is good, that thing is going to be about 1 over 0.4. Sorry, it's going to be about 4, right? 1 over 0.25. If overlap is bad, if the propensity score is getting extreme, that term is going to be blowing up, right? So it's the product of that inverse with the density ratio for moving from P to Q. And again, we can think about P to Q as being well-behaved when the target population is similar to the source population. It's going to be less well-behaved when they're far apart, when it's difficult to move from Q to P. Okay. So we're going to use this mapping, the implied weights, the implied weighting representation, to try to understand what our outcome model is going to be doing. Okay. So since I know that estimating my outcome model in this form is estimating the Riesz representer in this form, I can infer two things almost immediately. The first thing is that this parameterization is going to give me low confounding bias that's due to regularization for any target. Why is that? Intuitively, forget about the outcome model for a second and just think about trying to directly represent the Riesz try to directly estimate the Riesz representer and using a model that's going to let n be something. Well, if I regularize that nuisance parameter m, I know that the true value I want to get back is 0. So I can regularize the heck out of it. I can not regularize it at all. Doesn't really matter. I'm going to have low confounding bias due to regularization because the true value is 0, right? So if I shrink that thing to be smooth, I'm automatically shrinking it back to the truth.
Jared?
Okay. Yeah.
Jared, you're going to have about
Yes.
10 minutes.
Great, thank you. The second thing that I'm going to know is that I'm going to have large regularization bias when it's difficult to generalize from the overlap population to the target, right? Why? If that term TA of x is extremely variable, if it's extremely non-smooth, I'm going to have a bad time. There's two ways that can happen. I can have crappy overlap between treatment and control groups, or I can have a target population that looks very different than the source. Okay. So my main result is going to be that not only is the true Riesz representer in this form, when I estimate an outcome model in the R parameterization, my estimate for the Riesz representer is also going to be approximately in this form. So if we take all those empirical averages and substitute them with population averages, this equality becomes exact. Okay. So these are my estimates for MA and my estimates for TA. Okay. This TA I'm going to tell you about in a second here. This form is not very illuminating, so I'm just going to run through it. Why does that happen? It happens because that covariance matrix that you guys saw in my definition of alpha hat is going to be diagonal. So what I've done is I've diagonalized that matrix C. Okay. This scatter matrix is going to be block diagonal. The cross covariance between my features phi m and phi tau times that residual, right? So that residual, that term in red, shows up because we moved into the Robinson parameterization. And this guy is going to be equal to 0 by the properties of the propensity score, right? So I block diagonalize these things. That nice form on the previous slide falls out. This is related to the property of name and orthogonality. So in particular, when you have this property here, this orthogonalization property, that's equivalent to having name and orthogonality between my estimates of heterogeneous treatment effects, both in the kernel ridge outcome model and in the kernel ridge model for the Riesz representative. Okay, name and orthogonality, we all know and love it, does all kinds of nice things, including gives us robustness. Okay. So real quick, let's run through the punchlines. So again, we're going to continue to assume that the true outcome function is in the Robinson parameterization, no loss of generality. For any weighting estimator, I can decompose its bias into two pieces. On the left-hand side, we have confounding bias. That's imbalance between treatment and control groups. On the right-hand side, we have target bias. That equation is inscrutable. But what it's doing is it's measuring the difference between weighted averages and the target population. Okay, I'll unpack that for you in a way that's hopefully a little bit more clear in a second. We can study each of those two pieces independently. For our particular weighting estimator that has this form, what can we say? The first thing we can say is that the confounding bias is going to be approximately 0. Why? Again, because we pick up that residual term in the middle of that expectation. So just by iterated expectation, I know that that guy is 0, regardless of what that parameter m is. Okay. So my estimate, alpha hat, is going to mean balance almost anything between treatment and control groups. It's going to inherit the balancing properties of the propensity score. Okay. Again, that's going to happen because alpha hat has this particular form. Alpha hat is giving me back balancing weights. Okay. Balancing weights in the sense that they're proportional to that residual. Okay. What can I say about target bias? Target bias is going to have this particular form. It's going to be the expected value of this guy. Couple of other things we need to introduce here. The first one is what's called the overlap population. Okay. So the overlap population is just my original population from which I have IID samples, reweighted by this measure of overlap, E of x times 1 minus E of x. Okay. This function nu q over here is the target to overlap density ratio. So it's going to be a measure of how difficult it is to get from the population where I have overlap to my target q. My target bias is going to be the difference between an implied estimate of that density ratio and the actual thing when I take the expected value hitting that thing with tau. Okay. What can I tell you about tau hat? I can tell you something really nice. I can tell you that tau hat, or sorry, not tau hat, nu hat. I can tell you that nu hat is a direct estimate of that density ratio. This is just the Riesz loss down here. The regularization looks a little bit weird, but it's the same basic idea. I'm going to try to directly estimate that density ratio. So if that density ratio lives in h tau, my Hilbert space in tau, I should be able to do a good job as long as it's a smooth element of h tau. That's an insight I can use to debias. Big picture, what's happening here? The target bias is also going to be low if the overlap population and the target are close. If they're not close, I can pick a kernel that makes them close. Not going to have time to talk about that. All right. So those are the two sort of headline results. There's a direct mapping here between kernel ridge regression and Bayesian models. We get there through Gaussian processes. Okay, we're bumping up against time, so I'm not going to have time to outline that carefully for you. But the basic idea here is that if I have a Gaussian process regression model, I have a model that is centered at kernel ridge. Okay, how often do I have a Gaussian process regression model? Almost all the Bayesian models you know for causal inference can be recast in this form, including BART, BCF, et cetera, et cetera, et cetera. Okay. That's a fine point. Really briefly, how does that mapping work in the context of tree models? Regression tree models are going to work by ensembling short regression trees. In panels A and B, I'm just showing you what a regression tree looks like. We have the regression tree up top. That's the same thing as a partition of covariate space down bottom. We get our regression predictions by returning these little parameters mu. On the right-hand side, I'm just showing you how we build that feature mapping, right? So we take covariates X, we map them to dummy variables that indicate where I fall inside of those trees, and then I stick those dummy variables in a regression function. Okay. How does an ensemble work? I'm going to do this a whole bunch of times. That's what those tree features are going to look like. So when I fit a BART model, when I fit a BCF model, I know what I'm doing now. What I'm doing now is I'm solving a weighting problem. I'm trying to mean balance between treatment and control. I'm trying to target balance between my source and my target. I'm doing that in this tree space. This tree space is very robust in the sense that it's approximately invariant to transformations of my outcome. You can think about it as coarsening my covariates and then doing some almost exact matching down inside. Can't really tell you too much about that right now here today. Happy to talk about it later, maybe in the discussion. Some pictures for what it looks like. Before I leave, I just want to show you what we can do. We can do things like extract the weights for estimates of, say, average treatment effects, subgroup average treatment effects from an actual applied data analysis, right? So I'm showing you pictures of the weights for two different estimands, an average treatment effect, a subgroup average treatment effect, okay? I can look at them. I can see some interesting things right away. The weights for the ATE seem well behaved. The weights for the subgroup ATE maybe a little bit less. We have some negative weights. We have maybe some extrapolation. I had no idea that was happening before. I had some idea, but I didn't really know how bad it was. Now I can actually interrogate the weights. Okay, I can look at the distribution. I can see the regularization in action. I can fit a complicated Bayesian non-parametric model, and I can do balance checks, right? So I can look at balance between treatment and control and the original covariates. I can look at balance between treatment and control in a blown out covariate space. Okay, so I'm using here a parameterization of a Bayesian tree model in the Robinson parameterization. It balances a bunch of things that it has no business balancing, high degree polynomials, interactions between high degree polynomials. That's cool. Had no idea it was happening before I started this project. Okay, I can do the same thing for target balance. Okay, and I can do the same thing in particular for target balance for weird estimands like subgroup ATEs. what I can do now is I can interrogate that model fit, and I can actually see the amount of weight that I'm putting on observations that fall outside the subgroup. It's a little bit surprising, and it's going to let me characterize how shrinkage is working in this super complicated Bayesian non-parametric model. Okay, huge upside from my perspective. Okay. So wrapping up, I'll just throw this slide right here. I won't say too much about it. I'll let you guys just kind of stare at it and read it for a second because I don't want to take any more time. Thank you so much for your attention, and thanks for coming today.
Thank you so much. So then maybe Rahul, maybe you can start sharing that.
Perfect.
Perfect.
Great. Is that a good size, or is that better?
Yes.
Okay, very good. Thank you for having me. Today I'll discuss this paper, a unifying weighting perspective on causal machine learning. Enjoyed it very much. I'm going to discuss, or I'll provide a summary of what I think are the main research questions, and then I'll discuss a couple of the points that I particularly enjoyed that are in this work. Let's consider a causal parameter I'll denote by tau, and it'll be a functional or a scalar summary of an underlying regression. This regression I'll denote by F following the authors. It is also the outcome model or outcome regression because it's the expectation of the outcome Y given the treatment Z in the covariance X. Then the treatment effect is the expectation of this outcome regression with treatment on minus this outcome regression treatment off. This work studies estimators that are based on an estimator of the outcome model. And so in particular, we could take as our estimator of the outcome model, kernel ridge regression. We would call that F hat. And then we can construct a natural estimator tau hat for the treatment effect. It's the empirical mean of the outcome estimator with treatment on minus the outcome estimator with treatment off. This estimator implies weights. In particular, for this choice of tau hat, it can be represented as an empirical mean of outcomes as reweighted by these weights alpha hat. One way to see that this must be the case is that kernel ridge regression has a closed form solution with a vector of outcomes y, and that'll be preserved when taking the difference. I think a couple questions arise. One is, what is alpha hat for different choices of F hat? Some previous works focus on kernel ridge regression with the product kernel. And in this work, the authors propose and analyze carefully the R kernel, which has great properties, and also many extensions connecting their results to Bayesian causal inference. A related question is, what does this tell us about imbalance? So previously, some authors had characterized a bias and balance trade-off, and now in this work, the authors decompose, interpret, and control the components of the imbalance using the R kernel parameterization. Let me now mention the points I particularly enjoyed. So one point I enjoyed, it was on the last page of the draft that I saw. The authors write, outcome model implied weights provide a common representation for comparing different outcome model classes and specifications. So for each F hat, whether it's kernel ridge regression with a particular choice of kernel, or whether it's one of its kinds of extensions closer to Bayesian causal inference, we now have more tools to compare them. And in particular, we can ask questions like, which regions of the sample space receive greater weight if we use a particular choice of F hat? For a particular choice of F hat, how much extrapolation is taking place? And that's important for interpretability. Finally, which component of imbalance could affect results for this choice of F hat? Another point I enjoyed has to do with clever kernels. So the authors write, the debiased model in the R parameterization is equivalent to regression on a clever covariate. One way to interpret this point is that by carefully designing the kernel for F hat in kernel ridge regression, we can control various things. We can control one component of the imbalance that the authors call the M imbalance. We can control another component, and sorry, I should mention that that's in some ways automatically controlled by using the R kernel. There's another component of the imbalance that we can control called the target imbalance, and the authors provide a way to augment the R kernel to deal with that one as well. And I think it raises the question of what are more properties we could possibly achieve by carefully designing this kernel for f hat. In my view, I think this is an interesting direction for future work. And maybe I'll pose as a question for the authors when I finish, what possible properties they hope to further achieve, or properties that have come up in their discussions and thinking that could possibly be achieved by designing this kernel even more carefully. So to conclude, given a choice of an outcome model f hat, that implies an estimator for the treatment effect tau hat, and hence weights alpha hat, according to a formula like we see here. A couple of my favorite insights in this paper are, first, that now we have more tools to evaluate how different choices of f hat deliver different estimators tau hat. And then also, we have this insight that by designing the kernel for f hat, we can actually control properties of tau hat. And I think that's a direction I'd like to explore further. Maybe now I'll hand it back to the authors. And I'd love to hear their thoughts, especially about the second point.
Thank you, Rahul. Maybe like the Jared and Avi, do you want to respond to the comments? And also maybe we can open up the question and answers if we still have time after that.
Yeah. Thank you, Rahul, for that discussion. And again, I much appreciation and love for your work extracting from that rough draft these insights. Your favorite parts of the paper are also some of mine. We had to go quickly through debiasing, but that result is interesting, right? Because we sort of know intuitively that if we want to generalize beyond the sample that we have in hand, or if we want to compute certain average effects, we know that the way we model heterogeneity has to be tailored to that, right? We know it in terms of kind of the ignorability conditions we need to satisfy, the covariates we need to have. But this very clear notion that target to overlap density ratio needs to be smooth in the RKHS of the treatment effect function. I had no idea to think about it in those terms before I got started. And then it turns out that just really maps directly onto a lot of these old results about regressing on clever covariates, which again, just regressing on Riesz representers. One of the more interesting parts of this project for me has been exactly how difficult it is to disentangle those two sources of bias, the confounding bias from the transportability or generalizability bias, whatever you want to call it, targeting bias. And I think there's a lot of work to do here for other estimands. How do we think about that for Kate, right? So for Kate, we have a similar weighting representation, but what does target bias even mean, really, right? And then if we go beyond that, models of continuous treatment effects. What about when we're looking at, incremental treatment effects, or we're looking at trying to estimate a marginal dose response curve? Can we do similar things, right, where we can write down the Riesz representer and try to take it apart and get at different pieces of the bias and control it? Are there additional ties to these, orthogonal moment representations to the Riesz representer? And then I guess I would just say finally that one of the really interesting parts here is that we can get not all, but many of the benefits of an augmented estimator here without having to leave augmented outcome world, which is appealing to me as maybe not a dyed-in-the-wool Bayesian, but a guy that has some tendencies. It's kind of nice to have coherent estimation and inference from that perspective, while still having all these nice properties that also translate to good frequency properties. So yeah, long way to say that the points you found interesting interest me too.
Maybe shall I read the question that is in the chat? So the question is about, are there any results on asymptotics for your approach?
There are. They're not in my paper, but they exist. So Rahul's work is where you want to go if you want to understand any of this for Kernel Ridge. Question I would have for him is, could you sharpen any of that, right? If we're specializing to the case where we have R kernels and things like that, my intuition says yes, but I haven't, been through any of the math. But he studied in depth that estimate of alpha you get from optimizing the Riesz loss. We have results for things like the R learner that kind of cast it in this balancing weights form. And of course, the theory is just the theory, right? It's just particular choices for kernels and things like that. So I think that there's probably some room for specializing and sharpening existing results. We haven't really done that in the current paper. Just understanding the point estimates, it turns out, is a non-trivial.
Yeah, I'd only add that, from the R learner and from that parameterization, I think it guides us in thinking about what are the approximating assumptions under which we would get a possibly sharper result. So it's, I think through your parameterization, it becomes immediate what the additional assumptions would be.
I think there is more of a comment than a question in the chat. Now it's like, the comment says, for BART and Bayesian trees, there are excellent papers by Veronika Rokova on this topic. Probably you already know them. Do you want to say something
yes,
about them?
that's true. Yeah, that's true. And I was remiss in mentioning them. I'll also include my colleague Tony Linero in the bucket of folks that have results about this. They're sort of in the traditional vein of semi-parametric Bernstein-von Mises results. It's a little bit tricky to get them out of BART models as opposed to generic Gaussian processes. There's some interesting interactions in how you specify those prior distributions over tree structures, splitting rules, things like that pop out of the theory. There's a whole long line of literature that I didn't actually have cited on my slides on sort of more traditional analysis of partially linear models. You can map the one onto the other. What we're doing is a little bit more general. It's kind of annoying to put back in the other space, but it's very related. And the solution in the partially linear model is exactly the Robinson parameterization. So it's a little bit, I'm a little bit chagrined that it took me so long to see that connection when we started this project.
Sounds good. If you want, we can. I have like a question that I would like to discuss with you, but Avi already told me that he doesn't want to discuss. So I'm still very curious about this question, which was from the beginning, which they were asking, why do you put this specifically in Hilbert or recurring kernel? I forgot actually, RKHS spaces. Could any Banach space also work? And you guys both answered, but do you want to maybe comment on it together, or also Rahul?
Sure.
I punted.
Avi, go ahead.
To be clear. No, I punted.
So there's a couple of reasons to think about an RKHS. Well, several. One is practical and computational, right? So computing that estimate alpha hat is dead simple in an RKHS, right? So that's thing one. Thing two is that a lot of the methods that you know and love, turns out, are doing kernel ridge in an RKHS. Or doing kernel ridge and therefore giving me estimates that live in an RKHS. There are pieces of that result that do rely on things that are really tied to living in an RKHS, in particular, the reproducing property, the fact that function evaluation is a continuous linear functional in H. That's important for a lot of things in terms of the balancing, right? Like I want to pass expectations into that inner product and then look at what happens. Can't always do that. There are probably ways to generalize from here. Not obvious to me what they are. I will sort of drop a marker to work that Avi's done on more generic weighting equivalences that go beyond ridge regularization. What happens in parametric or limiting cases, high dimensions, when we substitute, ridge regression for a lasso type regularization or other sorts. There's a lot of interesting stuff there that doesn't fall into this approach. Still in regression, so I don't know if you end up in a bigger function space, but yeah, your life is just a lot easier in RKHS.
Sounds good.
Okay, so maybe it's time, the good time to wrap up. Thanks so much for the great presentation, Jared, and also answering a lot of questions, Avi and Rahul, for the great discussion. So let me open up my slide. Okay, just let me put it bigger. So next week, we actually don't have seminar because of Thanksgiving. So please have a wonderful holiday for everyone. And after that, we're going to have Agent Chu from Stanford. He's going to talk about factorial difference and differences with discussion from Eric Hartman from UC Berkeley after the break. So I hope that everyone will come back to the seminar after the break. So thanks so much again to the presenters and discussants. So thanks so much for everyone.
Thanks, everyone.
Thank you.